All right, so it's time to learn how to do u substitution with definite integrals. And in order to go over this, I'm going to use the example from the previous video, example 3. So our function is sine of x times cosine of x. This function has a domain of all real numbers because sine of x and cosine x each have a domain of all real numbers. So we can take any interval we want. I'm going to choose the interval from 0 to pi over 2. So what we want to do is figure out the definite integral of this function on that interval. All right, so in order to use the fundamental theorem of calculus to do this, we need to find an antiderivative, right? And in order to find an antiderivative, we can use u substitution. So let me show you, I'm going to show you two different strategies for approaching this. Perhaps the more straightforward strategy to explain is to say, find an antiderivative using u substitution. So we did that in the previous video. We already showed in the previous video that the indefinite integral of sine x times cosine x is, and I'm going to use the first of the two versions that we did, 1/2 sine squared plus c. So what I'm going to do is I'm going to take the 1/2 sine squared. I don't need to use the plus c because all I need is an antiderivative. I don't need like the general antiderivative to apply the fundamental theorem of calculus. I just need one of them. So the sort of simplest way to explain this is you find your antiderivative using u substitution, and then you say, just use the theorem, 1/2 sine squared x, and we're going to evaluate that at pi over 2 and at 0. So we're going to get 1/2 sine squared of pi over 2 minus 1/2 sine squared of 0. And now we'll just use the fact that sine of 0 is 0, and sine of pi over 2 is 1, and this will equal 1/2. So 1/2 is the value of that definite integral. That's one approach, okay? But I want to show you another approach that I personally prefer, and I recommend it because it kind of takes the entire process of u substitution for a definite integral and just wraps it all into one whole u sub process where you make some extra substitutions for the limits of integration. Let me show you what I mean. Let's start over, 0 to pi over 2. Sine x, cosine x. So now we're going to do our u substitution. I'm going to use the version where u equals sine of x. So yes, so du is going to be cosine of x times dx. So what I want to do is convert this to an integral. I want to say actually equals an integral where I'm going to have u du, right? But I can't write 0 and pi over 2 here and here. And the reason is that these are x values. This is like x equals 0 and x equals pi over 2. When you look at a definite integral, I forgot to write the dx on the end. When you look at a definite integral, the dx at the end, or dt or du or d whatever, that differential tells you what variable you're integrating with respect to. And so this interval, like the limits of integration you see at the top and bottom, those are values of that variable. So if I'm doing a change of variables, right? If I'm changing this from x to u, and I've done a variable substitution and I've done a differential substitution so that my entire integrand and differential are in terms of u, I need to take that and apply it to the limits of integration as well. I need to find the corresponding u values for the endpoints of the interval and convert the interval from an x interval to a u interval. So I've got to take my two limits of integration, and I like to write them with the bottom one and the top one like this, and I essentially need to convert those. And what I'm going to use to convert them is I'm going to use the relationship between u and x. So if x equals pi over 2, u will be sine of pi over 2, right? You've already decided what your u equals, so what you're using is u, so you can just use that to calculate the value, the corresponding u value. So this is 1. And then for x equals 0, u will be sine of 0, which is 0. So when you do this, you've got to change the limits of integration from 0 to pi over 2 to 0 to 1. And now we can finish solving this. We'll do 1/2 u squared. And the beauty about doing it this way is you never actually need to undo the variable substitution. Like you don't need to stick sine of x back in here again because your limits of integration are now u values, and you can just finish this with the u values. Sorry about the bang. So we have 1/2 times 1 squared minus 1/2 times 0 squared, and that gives us the same answer of 1/2. Okay, so there you go. Essentially, you're doing the exact same work because what you were doing down here with calculating sine of pi over 2 and sine of 0, you would have been doing that up here anyway. So you're doing the same thing. It's just a matter of how you like to approach it. So with the second strategy, it has this nice linear sort of sequence of equals, right? This equals this equals this equals this equals this. Whereas with the first strategy, you need to go off onto the side, and you need to go and do some scratch work on the side to find an antiderivative. Sorry, not that one. You need to go find an antiderivative on the side, and then come back to the problem and see and carry it on with the antiderivative that you found. So the second strategy here is, in my opinion, a bit more like fluid. This is kind of more streamlined, but you're welcome to use either one.